Good morning. Moving on into some new topics today. Chapter 8, Angular Quantities and Rotational Motion. Let's take a look at the diagram to start off with here. What we have is an object rotating around a point O in the middle, and we're going to call that the axis of rotation. And what we have here is the radius of this circle that we're drawing out from our point P, and we have counterclockwise rotation. And so in our last topic on circular motion, we were talking about centripetal acceleration and centripetal force, and we used linear quantities to describe things like velocity and acceleration. Now what we're going to do is we're going to move into angular quantities. And so we touched on this a little bit with the lab last week, and our simulation was expressing angular velocity in degrees per second. And so the thing about that was that all points on a rotating body are going to have the same angular velocity but different linear velocities. So besides using degrees to describe angular velocity, another unit that we'll use is something called the radian. So the radian is a ratio of the arc length divided by the radius. So if we look here at this second diagram, B here, we have our point P has moved counterclockwise in the positive direction. Counterclockwise is positive. And we've traced out this arc length L. And so to find out how many radians that we've traveled through, we divide L by R. And there's some relationships to know about with radians and degrees and circles. Hold on. So in one circle, or 360 degrees, or also one revolution, we have 2 pi radians, and we're dividing a length by a length, so the radian is sort of a unitless value. So if there are 2 pi radians in one circle, we can find how many degrees equals 1 radian. So we would divide 360 degrees by 2 pi, and we get 57.3 degrees. So basically 1 radian is a pretty big part of a circle. There's 6.28 of them in one circle, or 2 pi. And if I have a value in degrees, we can convert it using this conversion factor of 1 radian is 57.3 degrees. So let's look at an example here. If a bike wheel rotates 4.5 revolutions, how many radians has it rotated? So for every 360 degrees, we have 2 pi radians, or 6.28 radians. And we would take the that 360 degrees and multiply it by 4.5 to find out the number of revolutions, and then multiply that by 6.28, and we would get 28.3 radians. In math, a lot of times they want you to keep your answer in pi, and I understand that it's more accurate, but in science and engineering, oftentimes we want to actually, multiply it out, because most tape measures don't have units of pi on them when we go to build things. Anyways, let's jump to, you can take a look at this example if you want. I don't think I'm going to talk about it. And there's the solution. And let's revisit the kinematic equations briefly. Here are the 4 kinematic equations that we have learned about earlier in this class. And what we have is a set of kinematic equations with angular quantities. And so I bet you can figure out what these angular quantities represent by comparing them to the linear quantities. For example, here we have omega, which is our angular velocity. And so the equation is identical. We plug in angular velocity equals initial angular velocity plus acceleration times time. And the angular equivalent of acceleration is alpha, or angular acceleration. And so what's different about this acceleration than centripetal is it's not center pointing, it's tangential. Meaning we're speeding something up, like we have a washing machine and we turn it on and the rate of revolution is increasing. So that's how this is different than uniform circular motion. So we'll be using these equations in this unit a fair bit. So you might be wondering, how do we find the angular quantities of displacement, acceleration, and velocity? So let's get into that. So angular displacement here, if we look at this bike wheel, it's rotating counterclockwise, and so with angular quantities, counterclockwise is the positive direction, whereas clockwise we would call that the negative direction. And we take, just like regular displacement, our final position minus our initial position, except our positions now are going to be in radians or degrees. And the distance that is traveled would be expressed as radians. So one thing to note here, if we do a complete revolution with displacement before, we talked about this idea that if you start the day and finish the day at the same place, well, then you have no displacement. That's not exactly true for angular quantities. If you do a complete revolution, you've certainly rotated through 2 pi radians, or 6.28 radians, or 360 degrees, or 1 revolution. So to get angular velocity, these equations ought to look really similar. Old school velocity was distance divided by time, and now what we're saying is just our angular displacement divided by time, or our radians per second. And at any moment here along this rotation, if we wanted to find the instantaneous velocity, because these are going to be average velocities, we would want to shrink our time interval down so it's infinitesimally small, and we would look for the limit as the delta t approaches 0 for that equation. Right. There were some tips there. I just talked about that stuff. So, moving on. Here we go. Angular acceleration is the rate at which angular velocity changes. So, final velocity minus initial velocity divided by time. Well, that's basically the same thing as final angular velocity minus initial angular velocity divided by time. So our delta v over delta t gives us our acceleration value. And that does remind me a heck of a lot of those equations, you bet. So you might be wondering, how do I go from linear quantities to angular quantities? Because we've talked about an object with a linear velocity in meters per second as it moves in a circular path. How would we describe the angular velocity of that object? Well, the relationship is pretty straightforward. You just multiply the angular velocity by the radius to get the linear velocity. And so here's that expression, my linear velocity, which is delta L over delta t. So we have a small arc length here in some amount of time, and that would be in meters per second. And when we multiply the radius in meters times radians per second, since radians don't really have a unit, you end up with meters per second. So simply take the radius, multiply it by angular velocity to get linear velocity and vice versa. We have talked about this, though. This is a review slide. 2 pi r over t to get linear velocity. That was the circumference of the circle divided by the period. And that depends on the radius, obviously. So what I've taught you so far, it's not like it's not true. We're just looking at this rotation in a different way. So we can describe all the points on the rotating object in a similar fashion. Okay, let's take a look at an example here. So what I'm going to show you here is how we go from a centripetal acceleration from our last unit v squared over r to an angular acceleration of omega squared times the radius. It's a really similar equation, and they're related by going back and realizing that the radius times the angular velocity gives us the linear velocity. So once we have that linear velocity, we're going to square it and divide by the radius to get this relationship. So a helpful table for you guys is going to be this. I'd probably write this one down in your notes for sure. It gives you these relations between the linear values and the rotational values. And to do this, though, you have to be in radians. You can't be in degrees. So if you're, for example, you're multiplying the radius times the angular displacement to get the distance in meters, you need to make sure you have that that angle in radians. If it's in degrees, it won't work. Here's another equation of use in this unit. Is going to be angular frequency. So frequency is conceptually seconds per, or cycles per second, sorry. And period down here is seconds per cycle. So they're inversely related. We have cycles per second, seconds per cycle. The cycle in this case is going to be 1 complete revolution, and so the angular frequency is our angular velocity divided by 2 pi for a rotating body. And our units of frequency are going to be these things called hertz. We'll use hertz a lot in this class, especially when we get to waves, and the units of hertz are seconds to the -1st power, which is 1 over seconds. And that should make sense because it's cycles per second. And so try not to get those confused. Period is the seconds per cycle. And those two values are related in this equation. Period is going to be equal to the inverse of frequency. So one of the coolest things about rotational mechanics is, once you understand angular velocity, acceleration, and displacement, we go to thinking about how does a force bring about that motion, and the forces involved for rotating bodies is something called torque. And I want to give you an example of how to find torque, but from a really basic perspective. This is pretty much it. Torque is the lever arm, so this R value with a little perpendicular sign, times the applied force. So I'm going to switch over to the document camera and work through some diagrams of torque, although I'm running out of time. I think I need to make another video.